Imagine you're trying to teach someone how to drive a car.
Okay.
Right, so they get behind the wheel, they navigate downtown traffic for like 30 minutes. And at the end of the test, all you say to them is fail.
Just fail. Nothing else.
Just a simple binary fail.
Yeah.
I mean, you don't tell them if they ran a red light or if they sped through a school zone or, if they just forgot to use a blinker.
Right.
It's just a completely useless way to teach a human anything. But right now, according to the source material we are unpacking today, that is exactly how we have been training some of the most advanced AI agents on the planet.
Yeah, it really puts the problem into perspective.
Welcome to the Deep Dive. Our mission today is to explore the absolute cutting edge of generative AI. We're looking at a state-of-the-art research paper about something called MagicGUI-RMS.
Which is quite a mouthful.
It is. But if you're wondering what that actually means, the focus here is on AI agents. Basically, AI systems designed to interact with graphical user interfaces just like a human would.
Right, clicking around apps, scrolling websites, that kind of thing.
Exactly. I mean, think about how many mundane digital tasks you do every single day. Booking tickets, checking the weather, online shopping. Okay, let's unpack this. We're talking about an AI that can handle any of those tasks for you without just completely breaking when an app updates its layout.
Yeah, and to understand why this paper is making such huge waves in the AI community right now, we really have to look at the severe limitations of the current tech.
Because they're hitting a wall.
A massive wall. I mean, multimodal large language models like GPT-4o, for example, have these incredible vision capabilities now.
Right, they can see the screen.
Exactly. They can process a screenshot, parse the layout, understand the difference between a text block and an interactive button. But going from just passively seeing a screen to actively taking actions on it.
That's the bottleneck.
It's a huge bottleneck. Historically, developers have had to rely on, well, really expensive human annotations.
So literally paying people to click stuff.
Yeah. Armies of people clicking through apps, recording their screen and their cursor movements just to build these massive training data sets.
That sounds incredibly slow.
It is. And the alternative is to hard code very rigid static rules. But, those fall apart the second an app developer pushes an update and moves a button like 2 pixels to the left.
Right, because the AI is just blindly clicking where it was told the button used to be. But wait, if human annotation is that expensive, there must have been shortcuts. I mean, didn't they try just giving the AI a massive list of instructions and hoping the large language model could just figure out the interface on the fly?
They did, yeah. And honestly, tracing the failure of those shortcuts is it's crucial to understanding the MagicGUI-RMS solution.
So what were the attempts?
Well, the source material breaks down the evolution of these GUI agents into 3 distinct generations. That first attempt was exactly what you just described, prompt-driven systems.
Like a pageant, right. I remember reading about that.
Exactly, like a pageant. So developers relied heavily on feeding these really complex, handcrafted prompts into commercial models. And there is an advantage there.
Strong zero-shot performance, basically.
Right. The AI can sometimes just intuitively guess what to do on the first try without needing to be trained on that specific app beforehand. But because the prompts are manually engineered for very specific layouts, they're fundamentally brittle.
So if a website redesigns its navigation bar,
the prompt doesn't match the visual reality anymore, and the agent completely breaks down.
Man, that means you're constantly rewriting prompts for every single minor app update. That just sounds exhausting.
Completely unscalable.
So I imagine the next logical step was to try and train the models directly on visual data to bypass the prompts.
Yeah, that brings us to the second generation, which is supervised fine-tuning systems, or SFT models like OS Atlas or UiTARS fit in here.
Okay, so how do those work?
Well, instead of manual prompts, you train the AI on massive static data sets of recorded human interactions. It's kind of like forcing the AI to memorize millions of flashcards.
Oh, like here is the screen state, here is the exact correct action.
Precisely. And it really does improve the model's ability to ground its understanding in the actual visual elements. But again, the data set is static.
Right. It's just memorization.
Exactly. The AI learns the flashcards perfectly, but it really struggles to generalize. When it hits a highly dynamic layout or a totally unseen interface, it just lacks the underlying logic to adapt.
I see the pattern here. We went from brittle prompts to rigid memorization. And I'm guessing the third generation is where that driving test analogy comes back into play, right?
You got it.
If we can't hard code it and we can't memorize it, We have to let the AI explore and then just grade its performance.
Right, the third generation is rule-driven reinforcement systems. You drop the AI into an environment, let it explore, and a rule-based system gives it a reward, depending on the outcome.
But just like the driving test, it's only giving these coarse binary signals.
Yeah. I mean, the AI attempts this complex 10-step task like booking a flight, and it only gets a correct or incorrect signal at the very end of the whole thing.
Wow.
It completely lacks fine-grained diagnostics. It can't tell the AI why it failed. Like, did you click the wrong coordinate, or did you fundamentally misunderstand what the user wanted?
Okay, but wait, I have to push back on the core premise here for a second.
Yeah.
Haven't we essentially solved complex reasoning with massive models by now?
What do you mean?
Well, we have AI that can write a perfectly coherent, structurally sound, 1,000-word essay in seconds.
Sure.
If an AI can understand the nuanced structure of human language to write a novel, why does it suddenly struggle to just figure out how to click a shopping cart button? Functionally, a clean user interface seems way less complex than a novel.
What's fascinating here is that assumption totally ignores the fundamental difference in the cognitive tasks at play. Reasoning in text versus spatial grounding on a visual screen, they are entirely different architectures for an AI.
Really? How so?
Well, when an AI generates text, it's operating in this closed sequential system, right? It's just predicting the next logical token based on massive linguistic patterns.
Right, the word prediction engine.
Exactly. But operating an app, that requires mapping an abstract semantic intent like, buy this specific item, to absolute pixel coordinates on a highly unpredictable dynamic 2D plane.
Oh, I see. It has to actually locate physical geometry in a digital space, not just generate a string of related concepts.
Yeah, and the deeper mechanical issue with current reinforcement systems is something they call decoupled trajectory evaluation.
Decoupled, meaning disconnected.
Yeah. In a standard setup, the AI's error detection doesn't communicate with its decision-making engine in real time. So if it makes a critical mistake on step 2 of a 10-step workflow,
It just keeps going.
it just keeps executing the flawed trajectory all the way to the end, where it finally gets that big fail grade. What the AI actually needs is an evaluator in the loop.
So I'm going to tap the brakes.
Exactly. An evaluator that can step in instantly and say, hey, the layout changed, that coordinate is invalid, recalibrate and collaborate here instead.
Okay, so having a single monolithic model evaluating itself at the very end of a task is clearly a dead end.
Mm.
We need real-time, step-by-step diagnostics.
Right.
So how do the researchers behind MagicGUI-RMS actually solve this? How do you build an AI that genuinely understands the structural physics of an interface?
They solved it by completely abandoning the idea of a single evaluator.
Oh, really?
Yeah, that's the core innovation of this paper. MagicGUI-RMS stands for Multi-Agent Reward Model System. They essentially split the evaluation process into 2 distinct models that work collaboratively.
Okay, 2 model.
And each has a highly specialized focus. So first you have the domain-specific reward model, or the DSRM.
Local expert.
Exactly. Think of it as the local expert. Its entire job is to check deterministic operational rules within the immediate environment. It asks really rigid questions like, is the bounding box of this button actually interactive?
Or does the app actually allow for a swipe action on this specific panel?
Yes, exactly. It checks the document object model of the app.
So the DSRM only cares about the immediate physics of the app. It's essentially just checking if an action is physically possible within the software's parameters.
Correct. But as we know, a physically possible action isn't always the right action.
Right.
And that's where the second model comes in, the general purpose reward model, or the GPRM. This model acts as the global arbiter.
Okay, so what does the global arbiter do?
It zooms way out. It ignores the specific pixel coordinates entirely. Instead, it checks the semantic intent and the long horizon dependencies.
So it's looking at the big picture.
Exactly. It constantly cross-references the AI's current state with the user's original request. It's basically asking, does this immediate action actually advance the user's overarching goal?
Oh, I like this. So to use an analogy, the DSRM is kind of like the grammar checker. It scans a sentence, ensures the verbs are conjugated, the syntax is valid, the structure is totally sound.
Right. It ensures the sentence can technically exist.
But the GPRM is the human editor. The editor sits back, reads the whole paragraph, and makes sure the story actually makes sense and answers the original prompt. Because the sentence can be grammatically perfect, but entirely irrelevant to the story.
That is a brilliant way to visualize the architecture, yeah. And the source material actually gives a really specific, real-world example of how these two models interact to prevent catastrophic
Oh, the
errors.
Meituan app example, figure 5 in the paper.
Yes, the Meituan app, which is a Chinese platform for booking tickets and services.
Let's walk through that specific movie ticket example because I think it perfectly illustrates the tension between the two evaluators.
It really does.
So the setup is, the user prompts the AI with a very specific instruction. Please help me buy 2 movie tickets for the film Time's Child for tomorrow.
Right, tomorrow being the key word there.
Right, so the AI successfully navigates into the app, gets to the specific movie page, and right at the bottom of the screen is this massive bright red button that says, Confirm Seat Selection.
Naturally, the AI is drawn to that.
Exactly. It proposes clicking that button to complete the task.
Now, in a traditional system, the AI just clicks it and the task is considered done. But in the MagicGUI-RMS system, the two evaluators intercept that proposed action first.
So what happens?
Well, first, the domain-specific reward model, the local expert, analyzes the screen. It checks the element properties and says, yes, the confirm seat selection button is valid, it's interactive, it's clearly visible.
It follows the operational logic of the booking flow.
Exactly. So the DSRM flags the action as true. It fully endorses the move.
The grammar is correct. The button exists. It can be clicked. Clicking it advances a transaction.
But, and this is crucial, before the action is actually executed, the general-purpose reward model steps in, the global arbiter.
And it checks the wider context.
Right. It remembers the user explicitly asked for tickets for tomorrow, and then it reads the finer text on the screen just above the button, which shows that the currently selected screening date is set for today.
Oh, so the global arbiter realizes the local expert is endorsing a fundamentally flawed action.
Exactly. So the GPRM overrides the DSRM. It flags the action as false because the timing completely violates the user's semantic instruction. If we connect this to the bigger picture of GUI agents, this hierarchical assessment is revolutionary.
How so?
Well, without the GPRM acting as a semantic safety net, an AI agent will constantly fall into what the researchers call visually plausible but operationally invalid traps.
Visually plausible, but operationally invalid.
Yeah, because multimodal models are heavily biased towards salient visual cues. The AI sees a big, bright confirm button, and it just wants to click it because structurally it makes sense, but it completely loses the plot of the actual request.
It's the equivalent of successfully buying a perfectly functioning, non-refundable plane ticket for the wrong year.
Exactly.
I mean, the action is structurally sound within the app's physics, but it is totally useless to the user.
Precisely. This two-headed system forces the agent to satisfy both structural validity and semantic truth at the exact same time.
Okay, that structural logic is brilliant, but it raises an immediate, massive logistical issue for me.
Which is?
Data. If you're building an architecture that relies on 2 highly specialized evaluators constantly checking each other, you need a staggering amount of diverse training data.
You do.
You need thousands of examples of the AI doing things perfectly, doing things slightly wrong, and doing things catastrophically wrong so the evaluators can learn the boundaries of failure.
Right.
And earlier, we established that paying humans to manually annotate all this is a financial non-starter. So how did the researchers solve the data drought?
They solved it by engineering what is essentially an automated data factory.
An automated factory.
Yeah, they created this highly scalable pipeline that synthesizes its own training data. The result is this massive data set they call MagicGUI-RMS 72K.
72,000 data points.
Exactly. And the brilliance of this pipeline is that it doesn't just generate random noise. It generates highly categorized smart mistakes across a whole spectrum of difficulty levels.
So they're deliberately breaking successful trajectories to teach the models how to recover.
Yes. They're reverse engineering failure.
That's fascinating. So how does the pipeline actually do that?
It uses 3 distinct mechanisms to synthesize this data. The first is rule-based verification.
Okay, rule-based verification.
The system takes a known, successfully completed task, and it computationally generates what they call hard negatives.
Hard negatives.
Yeah, these are actions injected into the training data that look completely visually plausible on the screen, like, clicking a button that looks identical to a real one, but structurally, they violate a strict underlying rule of the app.
Oh, okay. So feeding these hard negatives into the system forces the domain-specific reward model to become incredibly precise in its physical grounding. It forces the local expert to spot sophisticated traps.
Exactly.
Makes sense. So what is the second mechanism?
The second is structured perturbation, which they use to create easy negatives.
Easy negatives. How does that work?
The system takes a flawless interaction and simply alters the initial text prompt. So for instance, the original user prompt might have been, "Help me buy Nike shoes on JD.com."
Okay.
The AI flawlessly navigates the app, finds the shoes, and clicks buy. The researchers take that successful visual trajectory, but they alter the prompt in the training data to read, "Help me buy a Nike t-shirt on JD.com."
Oh, I saw that in the paper, the instruction substitution method.
Right.
But wait, why force the AI to learn from such easy synthetic mistakes like swapping a shoe for a t-shirt? Isn't that too basic to be helpful? I mean, I know multimodal models famously suffer from semantic drift, where they lock onto a prominent visual cue, like the Nike logo, and forget the specific item. But is this just a brute force way to fix that?
That is exactly the mechanism at play. And it might seem basic, but preventing semantic drift is literally one of the hardest challenges in vision language models.
Really?
Oh, yeah. By constantly feeding the general purpose reward model these easily identifiable intent mismatches, it trains the evaluator to continuously anchor its assessment back to the exact text of the user instruction. It aggressively punishes goal confusion.
So it trains the AI to stop taking lazy visual shortcuts.
Exactly. Now, the third mechanism refines the physical execution. It's called intention-centric grounding correction.
That is a lot of words.
It is, but basically, often an AI agent will have the correct semantic intention, like it knows it needs to click the search bar to proceed, but its spatial grounding is just slightly off.
So it clicks like 3 pixels below the active area.
Right. The pipeline automatically calculates and fixes those bad coordinates. This turns a failed attempt into a clean, verified, positive sample.
Well, that's clever.
And conversely, if the coordinate grounding is mathematically perfect but the intention was completely wrong for the task, the system flags it as a moderate negative.
So they aren't just giving the model a massive pile of data. They're feeding the domain-specific reward model this highly calibrated, balanced diet of easy, moderate, and hard negatives.
Exactly.
This must force the neural network to map out the exact contours of why specific actions fail in different contexts.
It does, and the empirical results really validate the approach. I mean, by training the evaluators on this synthesized spectrum of failure, MagicGUI-RMS outperformed GPT-4o by over 30 percentage points on complex, long-horizon tasks.
Wow. A 30 percentage point jump over a flagship commercial model is staggering.
It's massive.
Okay, so we have the two-headed evaluator architecture, and we have the automated factory synthesizing the 72,000 data points to train it. The final piece of the puzzle is how this operates in the wild. The paper describes this as a self-evolving agent.
Yes.
I want to understand the mechanics of how it gets smarter without human intervention.
This is the engine of the entire system. It's a concept the researchers call the data-reflux loop.
Data-reflux.
Yeah. It operates as this continuous, closed-loop process of co-evolution between the acting agent and the evaluators.
So let me guess the loop mechanics. The UI agent analyzes a screen. It proposes an action based on the prompt. Does the global arbiter immediately step in to grade the final result?
Not quite, because that would be reverting to the old decoupled method we talked about earlier.
Oh, right, waiting until the end.
In the data reflux loop, the local expert, the DSRM, intercepts the proposed action first. It checks the immediate operational validity. But here's the critical difference. If the DSRM determines the action violates a rule, it doesn't just output a fail signal.
What does it do?
It actively calculates the interface properties and proposes a corrected coordinate or action based on the valid elements present on the screen.
Oh, wow. So the grammar checker doesn't just cross out the bad word. It actually writes in the correct verb conjugation for you.
Exactly. Then the global arbiter, the GPRM, steps in. It evaluates the agent's originally proposed move, it evaluates the local expert's proposed correction, and it analyzes the overarching semantic goal.
So it has options now.
Right. The GPRM computes the optimal path and decides which action is actually the best one to execute. The winning action is executed in the environment, and crucially, that verified action is fed back into the UI agent's training weights as a high-quality positive sample.
Here's where it gets really interesting. The agent is literally generating its own verified textbook in real time as it navigates.
It is.
But the mechanism I find most fascinating is the conflict resolution. What happens to the neural weights when the two evaluators violently disagree on an action?
That disagreement is the actual catalyst for self-evolution.
Really?
Yeah. If the local expert flags an action as operationally bad, but the global arbiter analyzes the broader context and determines that the action is actually the required path to satisfy the prompt, the system captures that specific delta.
So it zeroes in on the conflict.
Right. That conflict is isolated, categorized, and added back into the reward model system's own training set.
Oh man, it operates exactly like an automated immune system.
That's a great way to put it.
Every time the agent encounters a weird structural edge case or makes a nuanced mistake, the two models mathematically argue about it, resolve the correct path, and then generate an antibody.
A targeted weight adjustment.
Right, an adjustment that permanently upgrades both the acting agent and the evaluators. They are continuously writing patches for their own blind spots while you sleep.
The system transforms from just a passive judge into an active engine for continuous improvement.
Incredible.
And there's one final architectural layer the researchers add to ensure the local expert doesn't get trapped by invisible mechanics. They inject something called explicit operational knowledge, or EOK.
EOK, I saw that acronym. But how exactly do you inject operational knowledge into a vision model?
You do it by embedding the underlying structural architecture of specific apps directly into the model's parameters rather than relying solely on visual processing.
Okay, so going beyond just what's on the screen.
Exactly, because apps are not just flat, static images, right? They have hidden hierarchies and operational rules. The source material highlights a great example using GEO maps.
Let's hear it.
Imagine you prompt the AI to find a nearby EV charging station. If the AI relies purely on visual cues, it just scans the main map interface. And if the specific button for charging station isn't currently rendered on the screen,
A standard vision agent will either hallucinate a coordinate or just freeze entirely.
right,
Because if you can't see the button, it assumes the button doesn't exist. It basically lacks object permanence.
exactly. But by injecting explicit operational knowledge, the DSRM is equipped with the app's structural blueprint.
Oh, I see.
It mathematically understands that to reveal the charging station icon, it must execute a multi-step sequence. First, it has to trigger the search bar component, which dynamically renders a hidden functional panel. And then it must execute a physical swipe action on that specific panel coordinate to scroll to the hidden categories.
Wow. So the model understands the concept of digital object permanence.
Mm-hmm.
It knows the required button exists within the software architecture, even if the pixels aren't currently rendered on the monitor.
Exactly. The injection of EOK forces the system to understand the true operational flow of the software, rather than just taking heuristic visual shortcuts.
That's huge.
And according to the paper, this specific mechanism improved the system's performance on the hardest, most complex navigational cases by up to 33%.
33%. That is a fundamental paradigm shift. I mean, when you hear companies talk about the next generation of digital assistants, it's so easy to picture a bot that just memorizes a specific sequence of clicks to buy your morning coffee.
Right, and then spectacularly breaks the day the coffee shop updates their app interface.
Exactly. But MagicGUI-RMS represents something entirely different. We were talking about agents that can logically reason through unexpected layout changes, mathematically deduce how to close weird pop-up ads, and flawlessly execute complex workflows because they actually understand the structural and semantic environment they're operating within.
Yeah, we are witnessing the transition of AI agents from reactive visual pattern matchers to deliberative structural reasoners.
So what does this all mean? Zooming out, MagicGUI-RMS proves that by abandoning the single evaluator model, by combining a domain-specific structural rule checker with a general-purpose semantic judge, and feeding their constant interactions through an automated self-correcting loop, we can finally build AI agents that truly master our digital environments.
We're moving away from models that simply look at our screens toward models that genuinely use our software.
It is a profound leap forward in capability.
It really is. But, if we connect this to the bigger picture, it raises an incredibly important, almost disruptive question for you to think about.
Oh, what's that?
Well, if these GUI agents are learning to navigate our digital world through continuous self-evolution, adapting perfectly to intricate human interfaces without human help, how long will it be before software developers realize human interfaces are the actual bottleneck?
Oh,
Right. How long until they stop designing apps with colors and buttons for human eyes and thumbs entirely, and start designing pure data stream architectures exclusively optimized for the AI agents that are doing the navigating on our behalf?
that is a fascinating and honestly terrifying shift to consider. I mean, If the primary users of software become autonomous agents, the entire UI/UX industry will have to pivot overnight, from designing for human aesthetics to designing for pure machine readability.
We might soon be entirely locked out of the very apps we rely on simply because we don't speak the language fast enough.
That is a deeply provocative thought to end on. Thank you to everyone listening for joining us on this deep dive into the source material. We hope you walk away with a much sharper understanding of the invisible architecture being built behind your screens. Keep questioning the digital world around you, and we'll catch you next time. Hopefully, without you having to take another driving test to get here.